Working with conflict.
Yeah. Does that mean no material class?
I'm in.
Hey!
Oh!
What?
All right.
Aye.
Okay, so last time we left off, I started into a eutectic microstructure. Excuse me while I deliver an exam. All right, so anyway, so last time we started off with the eutectic diagram for lead tin, right? Is that I think that's where we got. Did I draw the whole thing? Did I finish the lead tin diagram?
Yeah.
Okay. Put that one away. So, and yet there are still even more complex systems, such as the one I'm about to show you. The iron-carbon phase diagram, or actually what we're going to do is we're going to draw it as 6.69, the iron cementite, or iron carbide. So this right-hand side is going to be Fe3C. So there's a ceramic material made of iron and carbon, iron carbide, Fe3C, that forms at 6.69 weight percent carbon. So on the bottom axis we have weight percent carbon. It turns out unless you cool something incredibly slowly, so very, very much in equilibrium phase diagram, you don't get iron carbon. Okay, if you cool extremely slowly, you can actually get iron carbon. But even just normal slow cooling is going to give you iron cementite. So this is what we consider to be the iron carbon phase diagram. Your book actually shows another version that actually goes all the way to 100% carbon. But that one's not typically used very often. Okay. So it turns out that pure iron melts up here at, these are all in degree C, 1538. So above 1538, it's all liquid. Okay. And you know why we're doing the iron carbon phase diagram, right? What happens when you put carbon in iron? What do you make? Steel. Right? So it's probably the most important structural material.
Stronger than steel.
In our, okay.
Spider webs.
So, and this is about 1394. So below 1538, there's this little structure that's kind of like this. I'm going to exaggerate the sizes here, just so that you can see them, because a lot of these things are really tiny. That's probably too far. Okay. That's probably too much.
What's going on out there in the left, upper left corner? This is all solid. Can you like draw it?
So this is liquid. You know, you always know the very top is all.
No, I mean not solid, but like the areas that are shaded in.
So this right here is delta iron. That little section there is delta iron. So it's just pure iron. Right? It's a form of pure iron. This is alpha iron. This is gamma iron.
This has a certain amount of carbon in it.
Everything to the right does. But I mean, even if you just track along the axis here, right? This is 912. That's 1394, 1538. So pure iron above 1538 is liquid.
What's the line that comes out from the nub for delta?
We'll talk about that in a second.
Is that like, is there shaded in?
This temperature is 1495. Okay, it's a solid, it's a horizontal line. So what happens is if I have pure iron, heat it up to above 1538, it melts. It's liquid. As I cool it below 1538, again cooling slowly so that I can maintain equilibrium conditions, it forms a solid, delta iron, which is, I think, a BCC, yes, which is BCC. It's called delta ferrite. Okay, so delta because it's delta and ferrite because it's iron. So here. Delta ferrite. It gets down to 1394, it suddenly transforms into gamma, which is called austenite, and is FCC. Then pure iron gets down to 912, it undergoes another change to alpha ferrite, which is again BCC. Okay?
So you probably don't want to do materials and temperatures where it's going to change between those two things because the material itself changes.
Right. Which is why welding is concerned, as we talked about, you know, in the Liberty ships. Okay? So there's three different phases that iron can hold, pure iron can hold: delta, gamma, and alpha. But as I throw in a little bit of carbon, as I increase the amount of carbon, the space that's occupied by gamma expands. Okay, so that, and I don't have, do I have, yeah, okay. This point right here, let me sort of zoom in. I'll zoom in on that point there. Okay, this point, 0.1% weight percent. This one, 0.2 weight percent. And this point out here, 0.5 weight percent. So here we have delta. This would be delta plus liquid. This would be delta plus gamma. This is gamma. This is liquid. And since this one actually comes down further, this would be gamma plus liquid. Okay, so I've distorted the picture in order to blow it up enough for you to be able to see where everything is. Okay. This temperature here is 727 degrees C. This concentration right here is 0.02 weight percent. Okay, so a much smaller number. There's very little carbon that can be dissolved in alpha, or can be dissolved in the alpha ferrite. And this number here is 0.77 weight percent. Okay, oh, and I guess I should put the other ones in here. This is 2.11, and this is 4.30.
Is the 272 the temperature of that line?
727?
That's what it is.
Yes, that's the temperature of that line. This other line is 1148. Now, if I go to the iron-carbon phase diagram, you'll notice the temperatures are slightly different. The regions are the same for the iron-carbon phase diagram. Now, it looks the same in shape, but the temperatures shift a little bit.
isn't the iron carbon phase?
So this is the iron cementite phase diagram, right? It only goes up to 6.69. Okay. If you look, I think it's on the previous page and the next page is the actual iron carbon phase diagram. Yeah. And you notice the temperatures are slightly different. Okay. And basically, we don't care about anything above 6.69 because that's, you know, we don't work in that region.
Why are the temperatures? Because like if this is just like a subset of.
This is not a subset, that's the point.
Okay.
This is for cooling at normal, slow rates. You have to cool extremely slow in order to avoid the formation of this Fe3C. This is kind of like it's a line over here, okay? But it's essentially a phase of its own. So down here, is alpha plus Fe3C, not alpha plus carbon. And in here, I have gamma plus Fe3C. And we call Fe3C cementite.
Is it steel or no?
No, it's a ceramic. And then this is gamma plus liquid, and this is liquid plus Fe3C, and this is alpha plus gamma. I think I've labeled all my key features there.
And once you get to 6.69, then it's 100%
Cementite. It's this sort of ceramic material. It's essentially a brittle form of, I mean, it's an ionic combination, right? So you use, iron here has, well, it's got a mixture, right? Iron has a mixture of valences, right? Because iron can be +2, +3, or plus Fe2O3, +3, FeOs, +2. So iron can be either +2 or +3, I think. I think that's what it is. Yes?
So looking at this, it appears to me at least that nowhere do we actually have iron in a usable temperature.
Not wrong. Oh, pure iron?
Yeah, like we don't actually have iron that we can just use to make materials. So
Unless
like,
it's pure. Right, this
Okay.
thing goes all the way down to 0.
okay.
But pure iron exists as pure iron, as alpha ferrite in the equilibrium conditions at room temperature.
But then steel, we don't have any pure steel then.
So realistically, we don't have any pure steel at room temperature. Right, steel, well, I mean, we do. Steel is a mixture of at least alpha and Fe3C.
Okay.
Okay, that's what steel is.
So alpha iron is really the only iron, or alpha steel, I guess, is the only steel we'll work with.
Alpha iron
Yeah.
is the only kind of homogeneous iron that exists at room temperature in equilibrium, under equilibrium conditions.
Okay.
And even then, if there's even a little bit of carbon in it, it will actually not exist as a homogeneous material, at least at some level, at the grain level,
Yeah.
because it'll be a mixture of these two materials. We still call it steel, but it is not a uniform composition of one thing. Okay? Make sure I'm not getting too far ahead of myself. Today's Monday, right? Yeah, okay. So, we have a couple of interesting points on here. This point right here, the 0.77 weight percent carbon, that we call the eutectoid. Eutectoid. Because it's eutectic-like. Remember the eutectic that I had for lead tin? Is where it transferred, it was an allotropic transformation from liquid to 2 solid solution phases. Remember that? Well, here, this is a eutectoid. It's an allotropic transformation from a solid gamma phase to a mixture of 2 solid solution phases, Fe3C and alpha. It was going from 1 solid to 2 completely different solids at a single temperature composition. So it's like a eutectic, except it does it from solid to solid instead of liquid to solid.
Are there any observable macroscopic changes when something like that happens?
Are there any observable macroscopic? Yeah, we'll talk about microstructure next time. So whatever day, Wednesday, we'll talk about microstructure. So we can explain what happens and why that's actually a good thing. Let's see here. So that's a eutectic. This thing over here, where it's doing just the opposite, right? There's an allotropic transformation from one phase to two different phases as it heats instead of cooling. This is called a paratectic. So it goes from a single phase to a liquid and another solid phase. And then there's also a paratectoid, not on this graph. That's something that looks like this, where warming it up goes to two phases, but where both the other phases are solids. Okay, so we have a eutectic, which is, this is a eutectic. It's going from liquid to two solid phases. This is a eutectoid. It's going from solid to two solid phases. This is a paratectic. It's going from a solid as it warms to a liquid in another solid phase. And then a paratectoid would be if this was another solid. So there's 4 different kinds of these unique single point transformations. Okay?
Where's the eutectic on there?
Right here. Liquid to 2 different solids.
And then eutectoid is solid?
Solid to 2 different solids. Solid 1 to solid 2 and solid 3.
And then paratectoid would be if it was going from a solid to 2 different solids.
It would be going from a solid to 2 different solids upon heating.
Yeah.
As opposed to a eutectoid, which is a solid to 2 different solids upon cooling. Okay? Okay, does that make sense to everybody? At least the words, at least you understand the words? Eutectic, eutectoid, paratectic, paratectoid. Eutectic and eutectoid are the ones we most commonly use. Those are the ones that probably. You can imagine, we don't do a whole lot of work with this part, right? Because first of all, I have to heat treat to really hot temperatures to get that. Second of all, if I cool it down, I'm still got to get it back to room temperature at some point. Right? So I've got to, I'm going to go through this region. We don't use much delta iron. Right? Delta ferrite is not a commonly used thing because it doesn't really exist very abundantly at room temperature. Turns out there are things we can do to make camphor exist at room temperature, but we'll talk about that later. No, not magic. Okay, so is that, those distinctions kind of make sense to everybody? Okay. This is probably the most important phase diagram for you to know. Iron-carbon phase diagram is probably one, because again, structural steel, you know, your welding stuff, you need to know what you're doing to something, and from an engineering standpoint, you need to know, am I changing it? So in other words, if I weld something by heating it up above 727 degrees, then I almost assuredly have moved it, changed its microstructure. Because even whether I'm out here or in here, the only place is if I'm less than 0.02% carbon, right, which is very little carbon. If I have any appreciable amount of carbon in there, then I undergo a transformation at 727 degrees. And at that point, I change the properties. Because going from a BCC to an FCC, or a mixture of 2 phases to a single phase, there's a lot of changes that can happen. Yeah.
Are we going to be able to need to be able to draw this or label it for the test or anything like that?
You probably need to be able to label it. You don't necessarily have to be able to draw it, but you need to be able to identify the different regions. And probably the 2 numbers that are most important, most critical, are the eutectoid numbers. So this one and this one. Those are probably the 2 most. This would probably be the 3rd. Okay. And then, well, I suppose, okay, I'll give you a 4th. This is sort of fundamental to the diagram. If you can do most, if you know those numbers, you can usually work around, pretty much find your way around most of All right, any questions?
What is ENP352? Is it BCC, FCC?
I don't know. It's an ionic compound, so it's got a coordination number. You know, it's back to being a. You know,
Sorry.
and I mean, so it has a crystal structure, yes, but I honestly don't know what it is.
But so as we go, say not at the eutectoid point, but somewhere else, even if we go from there to 727, about all of the alphas are changing to gammas.
So if I go, you're saying if I warm it from here to here? So I warm it from here to here, then yes, assuming into it, you know, at equilibrium. Okay, again, these are equilibrium phase diagrams. So typically I actually don't go from here to here. I'm more likely to cool it than heat it gradually. Okay, so I'm more likely to say, well, I'll start out with a liquid and work my way down, then start out with a solid and work my way up. Okay, but yes, if you let it rest long enough for it to come to equilibrium, indeed, all of the alpha will disappear and it'll all become gamma once I go above that line. But if I go above the line over here, only some of the alpha, there's essentially all the Fe3C becomes gamma, plus some portion of the alpha.
So welding does not follow any of this pattern. Welding brings it by a different path up to liquid.
We'll talk about the way the welding, we'll talk about the kinetics of the process on Friday, I think. So we'll talk about the kinetics of the process on Friday. But yes, you're right, welding takes you from the ground up, but it does it quickly. And so it doesn't actually follow the equilibrium phase diagram. But if you think about the fact that I take it up to if I'm actually up here in liquid, so I'm actually getting my steel hot enough to melt it, and then I cool back down, the cooling process you can still approximate as following the equilibrium phase diagram. It's just air cooling, not being quenched. Okay, any other questions? All right, then I want to go through a few problems just so we can kind of get acclimated to the process of doing using phase diagrams. So here we have the copper nickel. Remember I talked about that last time? And these are all temperatures in degrees C. Yeah, so I think that's pretty much everything that I had.
Can I go back and ask
Yeah.
a quick question actually?
Okay.
Is that 4.30, is that a eutectic point?
Yes,
Is that
that's a
what you get
eutectic.
everything to the solid?
Right. Okay, so basically what that means is the lowest temperature at which steel can melt is 1148 degrees. And then it's only if it's 4.3% carbon. Okay. If it's less than 4.3, if it's like 2.5% out here, it'll begin to melt, but it'll become slush. Right, so if I get up here, I've got a mixture of gamma and liquid. Does that make sense? So I get this slushiness, kind of becomes soft, but not really liquid.
So when it's up there, if it's in the little nub there, if it's in the delta plus gamma, it's only delta and gamma, there's no L, right? Even though L is
Right.
over there, right? Sorry, the two
Right.
nodes between.
But at that concentration, it cannot be a liquid. Okay? All right, any other questions? Okay, let's move on to solving some problems. Calculate the amount of each phase present in 1 kilogram of a 50-50 nickel copper alloy at each of these 3 temperatures. So, what would I do? Where's the 50 point?
In the middle.
Right. So I would draw a vertical line through my diagram right there. Right, at 50-50. So at each temperature, I'm going to go, basically starting at the top temperature and cooling my way down. Okay. Now notice they have an atomic percentage nickel on the top and a weight percent nickel on the bottom. And those two differ because copper and nickel don't have the same molecular weight. Okay. But still, you generally they're designed around weight percent. They're just throwing that in there for initial basic information. Okay. Almost got it.
That was
Right
perfect.
here too. What's that?
Withdraw.
No, I figured he was praying.
Below, let me pass this funnel. Now looking.
Lord, I got two choices. I can pay attention to class or I can sit here and pray. I'm going to pray. All right. All right, so 1 kilogram, 50-50, 1,400. Let's start that one. 1,400. What is it?
Liquid.
It's all liquid, right? So I have, what I would have then is 1 kilogram of liquid. Easy peasy.
Lemon squeezy.
1,300 degrees C. What do I have at 1,300 degrees C?
Wait. Oh, the amount. Hold on.
Right, ask for the amount at each is. Not a percentage, the amount. 1,300 degrees C. Where am I now? Right, I got a mixture. Right, I'm in this two-phase region, the alpha plus liquid region. Right? So, what am I gonna?
Inverse lever rule.
Inverse lever rule.
So then, yes.
Okay?
But I think it.
Now it turns out these lines are pretty thick and fuzzy on this.
It looks kind of like the 50-50.
What characteristic, what values do I need to extract from this?
Amount, liquid, and amount.
Okay, what am I extracting from the figure?
Where it intersects the thick line.
Where it intersects the thick line. Which thick line? This one or this one?
Both.
Both. So let's say this intersection is 58, and this intersection is 46. Okay, so we have numbers. So, it intersects at 58 and 46. What do I do? So I'll draw this up here kind of. So we have this line going up here, this line going over here. There, very cool. Line going over here. Right, this is my 50%. And this value is 46, and this value is 58.
It's all the same.
Okay, zooming in on that section. What do I do?
I find the percent of solid.
So I find the percent of what solid? Alpha, right.
Okay.
One solid, it's a solid solution of copper nickel, we call it alpha. Okay, so percent of alpha. What's the percent of alpha? It is not 58.
It's CP. Whatever that is.
I'm looking at my notes, but I have no idea what they mean.
33.
What's that?
33.
Is it 33?
It's gonna be 50 minus 26 over.
Show me
33.
The concentration of.
Yeah, how did you get 33, Britt? That's the key.
I took the 50 minus 46.
So you did 50 minus 46 over
Over the spread, which is 58 minus 46.
minus 46. Forget that, so we took 50 minus 46, which is the left-hand length of the lever, right, the side closest to the liquid, divided by the full length of the lever to get the amount of solid. Right, it's the inverse lever rule. Your book just calls it the lever rule. I'm the one who calls it the inverse lever rule to remind you that this side governs the amount of this material, and this side governs the amount of this material. Okay, so I have 15 minus 46 is 4 divided by 58 minus 46, which is 12, which is 1/3. So is 1/3 my answer?
Or that.
It's a third of a kilogram.
Right, so 1/3 of a kilogram, or 333 grams, or 0.333 kilograms. They asked for the amount, not the percent. Okay? That's in the amount of alpha. Right, so now I found the amount of alpha. So how much liquid?
0.667.
All right. Just by process elimination. But if I took 8 and divided it by 12, I still get 2/3, right? It's the same thing.
Okay, and that alpha that we have is 58% alpha?
It is 58% nickel. So the alpha that we have, what we have here is 0.338 kilograms of 58% nickel in copper. So the solid solution, we have 333 kilograms, or 0.333 kilograms of solid solution. That solid solution is 58% nickel and 42% copper. Similarly, we have 0.667 kilograms of liquid,
Which is 46.
right, which is 46% nickel. Yes.
So, at the beginning, when it's liquid, it's 50%, it's one phase, 50% of each. At the end, it's one phase, 50% of each.
No, well, yes, at the end, right, I see what you're saying, yes.
Where it's solid, but then in the middle portion, as it's liquid and solid, those percents of liquid and solid are changing
Right.
somehow.
So, again, we're kind of getting into the microstructure a little bit, but what you imagine I've got this liquid stuff. And here's what I look at on a microscope, I see liquid. Right? Then, as I begin to cool past whatever would be there, maybe 1320 degrees, or whatever temperature, I start to get a solid forming. I get little bits of solid forming. Right, little precipitations of solid. But the solid that precipitates is nickel rich. Right, because at 50%, what comes out first is that stuff. That make sense?
Let's just nickel at a higher level.
Yeah, you can think of it that way, yeah, sure. And in this case, that works fine. Okay, so it's nickel rich. So that means that these pieces are 2/3 nickel, roughly. Right? Something like that, close to 2/3 nickel.
Does that mean that 2 out of,
No, that means that each of those is 2/3 nickel. Each of those is a nickel phase with 2/3 nickel and 1/3 copper. As it continues to cool, these will grow. And the bits on the outside that are plated on are going to be more copper rich than the piece that's on the inside. You see what I'm saying? So that if I were to take a sample and then, they'll continue to grow until they almost, fill all the space. So there's just a little bit of liquid left, right? There's still liquid in here, and the spaces in between. But the solids have begun to encroach upon each other. At that point, when I'm almost all solid, right here, right? The little bit of liquid that's left is very copper rich. Right? So that then once that solidifies, I end up with a lot of copper here. It's not a huge amount of copper, right? It's not like pure copper. It's whatever that works out to be, maybe it's 33% copper. 33% nickel, 66% copper. But what was over here was just the opposite. It was 2/3 nickel and 1/3 copper. So I have a graduation in concentration between these two regions. Now in reality, at these temperatures, the atoms are pretty mobile. And so if I do this, anything, you know, I'd have to go at a sort of a fairly rapid equilibrium cool. Right? I'd have to cool through there quickly enough that I didn't, you know, that I could actually get these things to precipitate and grow, but not so fast that I allowed the diffusion to happen because of thermal oxidation. So in reality, if I did this truly at equilibrium, then what would happen is it would equilibrate its concentration gradient as well. Does that make sense? Right, 'cause there's a nickel rich here and copper rich there. Those two there would be a driving force, a diffusion driving force at the temperatures we're talking about to make those help those to even out. But in the end, what's solidified is indeed 50% copper and 50% nickel. But it's not 50 copper, 50 nickel at every point in the granular structure. Does that make sense? Big long answer to your question. Okay. But we don't generally draw that level of detail on this kind of a diagram. Okay, we assume it's an equilibrium cool so that all the solid at the end is 50-50. We'll actually, yeah, if we have time, we'll get to the more complicated one. Well, okay, what about 1200? Right, it's all 1 kilogram of alpha, and that alpha is 50-50. Okay, easy, straightforward?
And the liquid is 50% the whole way.
At the top, yeah. So if I asked you to really answer this question, it'd be 1 kilogram of liquid, which is 50% nickel. Then the next question would be, I have 0.333 kilograms of 58% nickel alpha, and 0.667 kilograms of 46% nickel liquid. So you have to tell me how much of what phase and what the concentration of that phase is. There's 3 pieces of information you have to tell me in these problems. Does that make sense? Keep track of the three pieces. Okay. Now here's another one, lead tin, right? We talked about this last time, it's a eutectic material. So we have a crucible containing 1 kilogram of an alloy composition, 90% tin, 10% lead, at a temperature of 184 degrees C. Okay, so where am I on this diagram?
Just above the line.
Just above the line? What line?
Eutectic line.
The eutectic line, just above the eutectic line. Where?
And
90% tin.
Right, so I'm over here. Right? So, how much tin would you have to add to the crucible to completely solidify the alloy without changing the system temperature?
Oh, so you want to move to the right.
Right, so I want to solidify by moving to the right instead of by cool. Right?
97.5%. Right?
Right, so I have to get to 97.
Just over.
98.
Right, but you just do it for the boundaries. That's why they said 184 degrees. Means we're just above. Everybody understand the problem? Above the eutectic, so we have a mixture of liquid plus beta tin. Okay?
But we can approximate it as being, we need to get eventually 97.5%.
Right, so when they give you that, you just assume you're on the line and you're going to 97.5, right? The reason they give you these numbers that are close to the line is so that you can do those. So you can get exact values and not have to read things off the graph. Okay? So, how much tin do I have to add? How am I going to figure this out?
Well, our lead isn't going to change.
Right, lead isn't going to change.
So you set a ratio up?
So I have
Not
1
quite sure.
kilogram of 90% tin, and I want to get, what do I want to get? And I want to get to, somehow I want to get that into 97.5%. And as you say, the amount of lead that I have is not going to change. How much lead do I start with? start with 100 grams of lead, 0.100 kilograms, right? How much tin do I have to add?
Two point five equals, 2.5 over 100 equals 100 over what? And you can find out the number of grams.
So if you're saying,
Find out the
using
total.
this, I end up with, you're saying 2.5 over 100 is equal to
100 over.
0.1 kilograms over X.
And that'd be the total value, and you just subtract.
Right, so does that make sense?
You're right.
What he's doing is calculate,
With 2.5 comes to about a percent of.
so if it's 97.5% tin, then it's 2.5% lead. So this has to become 2.5% of my final solution, of my final product. That 100 grams of lead, when it reaches 2.5% of my total mass, I will cross that line and solidify. Make sense? So now I got 2.5 over 100 equals that over X. Solve that, X equals 100 divided by 2.5, which is equal to 40 kilograms. No, 10, 4 kilograms, sorry. 100 times 0.1 is 10.
Wait, so,
What does that help? That's lead.
wait,
Isn't
So
it
you
given
need
So what is X?
total
Total.
volume.
Total mass.
So you need 3 kilograms of tin.
So that means I would have, no,
That's how much you would add.
that is not how much I would add. That's the total mass that I would have at the end.
Yeah, so you need 3 in the end, because you would do 1 kilogram minus, or
Nope.
4 minus 1.
No, it's 0.1 kilogram.
Oh, you guys see what you're saying.
Because we're adding.
3,900 grams of.
Right, right, so that means that I would have, but I started with, I see what you're saying. I started out with 1 kilogram, and I have to end up with 4 kilograms, which means I have to add
3 kilograms.
3 kilograms of tin, right? Or I can look at it and say, I therefore have 0.9 kilograms of tin to begin with. I have 4 kilograms in the final product. I still have my 0.1 kilogram of lead and my 0.9 kilogram of tin I started with. Therefore, I need to add 3 kilograms of tin. Does that make sense to everybody? Nope? Still staring. So, 4 kilograms total. This equals the final amount of tin plus the final amount of lead. But the lead hasn't changed. I haven't added any tin, or any lead. So Sn, the final amount of tin, is equal to 4 kilograms minus the amount of lead that I started with, which ended with, which is the same as I started with, the 0.1 kilograms of lead, or 3.9 kilograms. If I end with 3.9 kilograms of tin, and I started with 0.9 kilograms of tin, that means I had to add 3 kilograms of tin. Okay? Does that make sense? Now, in reality, that would be hard to do. Right?
Yeah, how do we add that tin? Do we add like a hunk of tin? Do we inject liquid tin? Or?
Yeah, you can because with, yeah, so I'm not sure, I'm not saying that's actually physically achievable.
It slowly diffuses in your fluid, probably.
So in reality, the liquid tin, or the liquid material has a lower density than the solid would. So if you did it slowly enough, put the solid in, it would drop and it would fall to the bottom, and it would drop and fall to the bottom, and so then the liquid would remain on top, but the liquid would become less and less as you have more tin in there sucking the lead out of the liquid. Kind of. Anyway, All right, I'm not saying it's really a feasible thing, I'm just saying this is the problem, and that's what we're doing, okay? Let's do one more, if we have time. Let's try one more. Okay, so here we have X-ray diffraction determines that a refractory brick has 25 weight percent alumina and 75 weight percent mullite. Okay? So mullite is this intermediate sort of ceramic material that's a mixture of aluminum oxide and silicon dioxide. So Al2O3 and SiO2 form this solid solution, kind of like we looked at with MgO and aluminum earlier. So I just have to wait 5 minutes. I'll be with you in 5 minutes. So does that make sense? All right, so there's this mixture, this special phase. Okay? And we're out here someplace. We have a mixture, 25% alumina and 75 weight percent mullite. Okay? We're out there somewhere. What is the overall silica content of this material? So what would I do?
Well, should we get our weight percents into mole percents? Because it's got molar percent on the bottom.
Right, so how would we get our weight percents into mole percents? Right, so the easiest thing is just sort of start with the baseline assumption that we have 1 kilogram in the brick. Right, that makes it easier for students to for you to wrap your mind around. So if I have 1 kilogram in the brick, how much alumina do I have? What's that? 0.25 kilograms. So I have 250 grams. So I would have 250 grams of alumina. How would I convert that into a number of moles? I divide it by the molecular weight of aluminum. So I divide that by 2 times the molecular weight of aluminum, which is 26.98, plus 3 times the molecular weight of oxygen, which is 16, and that gives me 2.45 moles. So I know how many moles of aluminum I have, right? So then, what's next? Do the same thing for mullite. I have 750 grams of mullite. What's the molecular weight of mullite? Mullite is a solid solution of SiO2 and Al2O3. Yes, ma'am?
There's a stoichiometry in the book that says is that, can you give us a monthly weight?
Yeah, sort of, except the stoichiometry is not exactly fixed. Right? Because mullite occupies a range. Right? There's a slight range in the mole percent aluminum in mullite. Alumina and mullite. So what I'm really going to use, I'm going to use the right-hand edge of this. Right? Okay, these temperatures are really hot, so we're going to use the bottom one because we're presuming that we're doing this at room temperature. Right? You don't usually do X-ray diffraction at 1500 degrees C. Right? So we're going to take this, that's 64% there. So what we have is we have 0.64 times 2 times 26.98 plus 3 times 16. Right, it's 64% aluminum. Plus 36%, 0.36, times SiO2, which is SI is 28.09 plus 2 times 60. Does that make sense?
Seems kind of weird. That molar is, yeah,
Mol-
203. I guess
Molar
at some
is a
point-
physical mixture, a molar mixture of Al2O3 and SiO2.
And then we're just mixing more AL203.
And we're just, and it's mixed with, right, because what happens is the Al2O3 separates, some of it stays by Al2O3 by itself, and some of it mixes with this SiO2 to form molite. Okay? But not all of it can form molite. You only have enough SiO2 to form a certain amount of molite. All that's left over forms alumina as a separate phase.
And that's more than just a way, so there's actually two different materials there. Molite has different properties
Than alumina does, yes. I mean, it's nothing different than what we've been talking about with the metals. Right? Lead has different properties than tin. But we have, in that bottom, below the eutectic, we have a mixture of lead and tin. And so it's no different here, it's just that they're ceramics, that they're compounds instead of pure elements. All right.
Or we didn't even talk about.
No, we didn't.
But now we know what molite is.
But we are out of time.
What is molite used for?
What is it used for?
I couldn't tell you off the top of my head.
Light things on fire.